Okay, hello everyone. Thanks for tuning in today. So it's my great pleasure to present Wang today. She is from Global Brain Research and is going to talk about Bayesian optimization and how pre-training helps to improve the performance of Bayesian optimization. So yeah, with that, the floor is yours.
Great, yeah, thanks, Sarah. Okay, so let's dive into this topic. Like, what does pre-training mean? What does Bayesian optimization mean? Probably the answer is clear to a lot of folks within the AutoML committee. But I think it's probably still worth to step back a little bit and actually think about what is Bayesian optimization. So the way I look at it is actually an abstraction of how decision making is done in a very intelligent way, and those decisions is abstracted to the way that we collect data and using the collected data to gain knowledge, so that you can collect data better in the future. So in terms of I think how people view BayesOpt and AutoML, my guess is we are trying to like use Bayesian optimization as a machine learning method to automate other types of machine learning algorithms, like for example hyperparameter tuning. And there's also like other fields that also consider BayesOpt as a subfield, like for example in optimization and more specifically global optimization. The way we look at Bayesian optimization is really to see like how we can use machine learning and more specifically like the Bayesian part of learning to help Bayesian to help the optimization process. And then there are also like Bayesian optimization for experimental design. And again, it's about how to use these Bayesian type of thinking and computations to help design the experiments better. So it's really about, well, we collect data and see what kind of knowledge we have right now, and then we make better decisions in the future. Okay, so let's probably proceed with this abstracted definition of making smart decisions. And if we think about Bayesian optimization this way, it's really a way that we can consider data collection in AI and machine learning systems. And the way, at least I think about these problems, is that there are two ways that our AI system is interacting with the world. On the right-hand side, we have the system interacting with our engineers, scientists, or any experts who have certain expert knowledge. So we have expert knowledge at one hand, and then you have another side of the story where our model tries to collect data from the real world, or annotators who tries to present certain labels to the data. So in my past research, the kind of trend I was observing is that you sort of have this required number of data points for learning, and then you have like the kind of expert knowledge you insert into our machine learning system. Then there's sort of like this kind of curve where if we look at the extreme cases, the zero expert knowledge will correspond to the tabula rasa methods. So we completely start from empty. And then on the other extreme, we have zero data required for learning. And that corresponds to no machine learning and basically just hard coding. And I mean, it's not like either cases are not really a bad thing. And then we have the middle ground, which is to learn with Bayesian priors. So I think we're closer and closer to how Bayesian optimization works now. So let's see. Here are some examples of like the way we think about Bayesian optimization with certain strong priors. And these are the work I did in my PhD, which tries to do robot learning as a way of Bayesian optimization or experimental design. And it really tries to, what it's doing is that it tries to scoop and pour a lot of times and then try to measure a score decided by the scale underneath those balls. And it relies on very strong expert knowledge and this kind of priors that they already have, like for example, the modularity of the method where it's it can't really learn every control commands of every time step. So we build in the notion of planar. And then there's also this learning step that we specifically encode to the algorithm, and it chooses which data points to collect in order to incorporate to the posterior so that it can make better decisions in the future. So eventually, I mean, what it tries to do is to use these learned models to make the certain choices on its planning trajectory so that it can eventually achieve relatively complex and long horizon goals. So for example, this example here is trying to achieve a very long horizon goal of serving broccoli. And then here we're talking about like how to make a cup of coffee. I mean, of course, like in a lab experimented way, how to make a cup of coffee with milk and sugar, which requires pouring, scooping, stirring. And each of the kind of action or skills are learned based on these Bayesian optimizations type of style of acquiring the data. But eventually we're going to incorporate those learned models in a way that tries to complete something of a bigger scheme. All right, so this might be a little controversial, but from the point of view of this particular talk, I wouldn't consider Bayesian optimization as a black box function optimization approach. And let me expand a little bit. So, I mean, the Bayesian optimization as an abstraction of collecting data, it doesn't really maintain any state in terms of like, oh, what my state is when I'm trying to collect the data. Actually, one can argue that the GP part is the state, but let's think about it as like a more abstracted level, like a banded approach. So what it does is it goes into a loop. It chooses the new occurrence points to evaluate. And once it gets the observations, it updates the model, and then it goes into the next iteration of collecting data again. So what's missing in this particular algorithm that completes Bayesian optimization is this initial part, which we start with a model. And this model typically is characterized by a Gaussian process, and it tries to tell you, well, how smooth the function is, what my understanding about these correlations are. And then that's how the Bayesian optimization approach can start with an initial knowledge and then tries to collect data to build on top of it. And then one might be curious, like, how do we define these initial models, which, I mean, we call it prior, right? So yeah, if we think about this particular question, it actually brings a paradox as opposed to like what we talked about, this relation between required data for learning and expert knowledge. So in the actual real world, when we are using Bayesian optimization, our goal is to optimize a certain expensive function with as few queries as possible. And I mean, the reason that we use it this way is because the Bayesian inference part is often, I mean, not as cheap as a lot of numerical methods. And then the priors are encoded by the experts who had the intuition about the kind of expensive functions. So for example, how quickly they are, how smooth they are, differentiability, things like that. So if the intuition is lacking, for example, when we are doing hyperparameter optimization of deep learning models, I mean, we don't even understand deep learning that well. How do we understand their hyperparameters? So in this case, I mean, we don't have a lot of expert knowledge, and Bayesian optimization needs more data, but actually requires expert knowledge to make good decisions on the data. And we enter into this scenario where, well, which I call the chicken and egg dilemma of Bayesian optimization. At one point, I mean, we need expert knowledge to have an initial belief on what are the regions that might be more interesting. And then on the other hand, well, the way that we build in expert knowledge is actually through getting the data and doing like type 2 maximum likelihoods. And it's really not ideal. So the question is, can we reduce both the data and the expert knowledge, which are kind of required, but maybe like we don't really have them. So we want to reduce our reliance dependencies on these data and expert knowledge. So although it seems not really possible from this particular plot, but there's a way to actually overcome it. And TLDR here is we'll do pre-training. And a lot of people might call it meta learning, learn to learn, prior learning. And actually, like I've been calling it prior learning for a long time. So the way we think about this is, well, instead of just the one row that we are looking at in terms of thinking about these machine learning algorithms, we actually have another row where, I mean, our machine learning or AI algorithm, more specifically in this talk, we're talking about Bayesian optimization as an embodiment of these approaches. We are not developing one model and not to touch it again, right? We're let it collecting data and without modifying anything. We actually go through this iterative development scenario where we as engineers or scientists or experts who are using machine learning, artificial intelligence, we are improving these prior models because we are gradually accumulating our experience with a certain type of problems. And by the next time we develop a new model, we have more expert knowledge. So one can argue that, well, as the approach itself, for the AI model part, we can also accumulate the knowledge. And the way we're doing that is to do meta learning or pre-training. And we can pre-train our prior of our current model so that we can make better decisions in the future. And those kind of priors really comes from in a very similar pattern to the expert knowledge accumulation, right? It comes from the past experience of our machine learning model with these types of functions. Okay, so a few concepts here. Prior learning itself is a relatively classic word that we describe, I mean, yeah, probably like how many years ago? Is it 30 10-ish years ago, people were already thinking about, well, how do we learn the prior? And they pointed out that, well, we're going to learn it from point sets, which is a set of IID sets of potentially non-IID points. I'll go back to this point later. And then there's pre-training, which is relatively a newer word, or like relatively newer in terms of popularity. And that's a procedure of learning these priors in a relatively non-Bayesian way. And it emphasizes this prior learning part, which happens before training the actual model. So I think intuitively for people not really familiar with like these Bayesian type of thinking, then pre-training is actually a much better word to describe what's going on right now. And then there's meta-learning. Yeah, I think roughly it's a frequentist way of calling prior learning. And then there's learning to learn, which is an interpretation of meta-learning or vice versa. Okay, so what does pre-training mean in Bayesian optimization? Let's scope down from the machine learning as a whole with like Bayesian optimization as a representative to the Bayesian optimization itself. So before that, let's look at what it means in the modern deep learning world, right? And so it's actually really simple. I mean, we have all these vision models from CNN to vision transformer, and the pre-training step typically means we train the model on a very large data set, like with certain loss that you define, and then we save the pre-trained model. Yeah, it's as simple as that. And then in the fine-tuning, we restore the pre-trained model and continue training the entire model or part of the model. So for example, a popular approach is actually to fine-tune only the head layer. And in this case, we're thinking about doing this on a relatively small data set, for example, Cypher 100, and then you have the fine-tuned model specifically for Cypher 100. So pre-training actually brought a lot of success in deep learning, and specifically we're talking about supervised pre-training for like image tasks. And so what we know at this point, looking back, is that pre-training on these ImageNet and fine-tuning on those ImageNet competition tasks actually led to one of the breakthroughs in deep learning. And this paper from Gershk, I hope I'm pronouncing it right, 2014, it says supervised pre-training on a large auxiliary data set followed by domain-specific fine-tuning on a small data set is an effective paradigm for learning high-capacity CNNs when data is scarce. So, and in this paper, they actually treat it as one of the guiding principles for the kind of deep learning practice in image object recognition and these computer vision tasks. So the model we have in Bayesian optimization is typically a Gaussian process. And so if we think about Gaussian process, I mean, it's a distribution over functions. And at first, I mean, our functions may look like the one from the left part, which is like the prior part. And they kind of follow a similar paradigm, but I mean, they're going to be very different. And eventually, like if we collect some data, like these black dots on the right-hand side, these are observations, and we pin down the observations, and then the posterior follow another paradigm, which they are going to be very close to the observed points, and then relatively flexible elsewhere. I mean, the reason that we love Gaussian process is that it's mathematically really nice, and it has a closed form posterior because we have conditional Gaussian, which means like the posterior itself is another Gaussian process. So I mean, the way that I think pre-training should happen in Bayesian optimization is to pre-train this particular Gaussian process. So given these many functions that potentially exist in our like daily life of like interacting with these expensive functions, we can utilize these interactions and these experience to train the Gaussian process before we do the Bayesian optimization part with relatively scarce amount of data. And the goal here is to train the model so that we can optimize how good all these observed functions fit the particular model. Okay, I'm gonna talk about how in the next. Is there any questions so far? All right, great. I think everyone's convinced. Okay, so let's talk about pre-training. And the way, at least I'm currently formulating it, which is a little different from what I did like 4 years ago, which is to think about it as a multitask Gaussian process, and how do we try to fit it better through the lens of hierarchical Bayes. So yeah, let's look at this. And here, each of the FIs correspond to one task. And I mean, basically each task is a function that we're interacting with. Yeah, notice here, I'm not talking about doing Bayesian optimization with, just we're interacting with. And then, so we have the main function, mu, and the kernel, which is k. So each function is sampled from this GP defined by the main function and kernel function. The key difference to our typical way of thinking about multitask Gaussian process is that here all the functions are IID samples from the same GP. So instead of learning the correlation among tasks in traditional multitask GP type of work, we're actually learning the Gaussian process that generated all the tasks. So going back to this notion of prior learning, which was defined as learning on point sets, a set of IID sets, potentially non-IID points. It's actually, I think, a really smart way to describe the scenario. So I think it's clear to us now in terms of what it means to Gaussian process. And basically, for each row, we have the non-IID points because they're from the same function. And for between all the tasks, these are the IID sets. So essentially, we're trying to learn from this set of IID functions where we have non-IID observations from each of the functions. Okay, so this is how it happens for Gaussian process. We train a main function, in this case hat mu, just to differentiate from the actual model with mu and k. And then we also train the kernel k hat, and we hope that it best fits the data that's generated from a Gaussian process with unknown main function mu and kernel k. Okay, so that's the pre-train step, and visually what happens is that we have all these color lines where we had some interactions with. So we know certain like observations from these lines. And we'll learn an estimated mean function and an estimated kernel function, the mu hat and k hat. Apologize for the small font. And then once we have it, we get the pre-trained model, we save it. And whenever we need to do Bayesian optimization, we retrieve these models and use those as the priors to solve the maximization or minimization problem using Bayesian optimization. Okay, so just for notations, we call each row, observations from each row as DFI. And we call all the observed data from each of the function as dn, which is a collection of these DFI. So it's a dataset of datasets. And what this means is that we're going to pre-train the min and kernel, which is our pre-trained Gaussian process, to best fit the dataset dn. And here's how it works. So, I mean, everything else is our typical Bayesian optimization, except this particular line, which is kind of similar to how you think about like pre-training in deep learning. So we're going to pre-train based on this dataset dn. And here I'm going to talk about two methods. One is what we call the empirical KL divergence, and then the other is pre-training with negative log data like this. So in terms of empirical KL divergence, let's first reduce this a little bit chaotic notations to something much simpler. So here, I mean, we have the inputs from each task, so which is like denoted as xji, and we have number of inputs from each task, which is mi. And let's think about a much simpler one. So suppose we have the same set of inputs across all the tasks, so all the x1 through xm. But here we have different like observations from each task on these same inputs, which are denoted by yij. So I correspond to the task ID, and j correspond to the input ID. If we take out all these yij's, you can see that everything else, like x1, xj, xm, they are the same for every task. So let's just take out these y observations. And for each task, so for each row, all we know here from the definition of Gaussian process is that there are some evaluations on a finite set of inputs, and they follow a multivariate Gaussian distribution where the mean is described by the mean function evaluated on these x1 through xm, and the covariance is described by the kernel function. And because we have the noise in the observations, so we add a diagonal terms for the noise. So it all seems very basic, right? And because this is a multivariate Gaussian, then what we can do is to estimate what the, I mean, yeah, through sample mean and sample covariance estimation, or you can do empirical base, maximum likelihood. And what you get is these very simple estimations of the mean vector and covariance matrix. So if we look at our model, we have like these mu's as vector and these k's as a kernel, the grand matrix. And what we don't know is the mu, k, and sigma. So we're in a fully unknown like GP scenario where we want to learn them. So the thing we can do here is to define the KL divergence between the multivariate Gaussian that we just estimated and the multivariate Gaussian defined by our model. So both are multivariate Gaussian distributions, and the KL divergence is easy to obtain. And our goal here is to optimize mu and, well, the function mu, the function k, and the noise variance sigma from this particular KL divergence. Yeah.
Sorry, quick question here. So your x, they need to be the same across tasks, right? So x1 is the same, yes, for f1 as it is for f2 or f3.
Yes, in this case, okay. Yes. But I'll talk about a more general case.
Okay. Cool. Thanks.
In a slide or so. Yeah, thanks. Right, so this is a simplification. And if we think about the more general case, the most straightforward way is to define the negative log likelihood. And in this case, we're very flexible on what kind of inputs we have. And they can have like different numbers of inputs for each task, and all these inputs can be different in different tasks. Yeah, hope that answers your question, Aaron. And because we know, yeah, and because we know all the FIs are IID samples from the GP, so our NLL is very well defined. We just need to sum everything up. And within each additive component, it's just really straightforward. I think, okay, yeah, it's just like really straightforward negative log likelihood for a marginalized Gaussian process. Well, the marginal likelihood for a Gaussian process. Okay. So this is actually the kind of message in this particular series of work where we talk about pre-training brought a lot of success in deep learning, but actually also helps Bayesianization too. So for this particular algorithm, let's first talk about the improved time and memory complexity. For the KL approach, it has an overhead of OM squared n for time. So we're gonna go quickly through these. So the overhead is to compute the estimated mean and covariance. And then for computing the loss function, it only takes OM cubic, and m is the number of observations from each task. So we have so the GD, gradient descent, SGD are just the way you can think about gradient descent as the approach to optimize it. Where you have k steps, you can also generalize to LBFGS, because we know roughly how much time complexity or memory complexity it is for each computation. And then for the NLL approach, the loss function computes in m cubic n, and n is the number of tasks. We can also reduce it to m cubic by parallelizing over all the tasks, since they're just additive. But this will also increase the memory complexity. So the thing to notice here is that typically multitask GP or contextual GP has O of m cubic and n cubic computational cost, but here we're reducing it to linear in number of tasks. Okay, so So we first looked at this problem in 2018, and the immediate thing I thought was to prove the regret bound. So we know that is that, well, we actually can get near zero regret with an unknown Gaussian process prior. So, I mean, that's really amazing, right? So far, I mean, I think prior to this, our 2018 work, I mean, we have a lot of like regret bounds in the community, but most of them, I mean, as far as I know, pretty much all of them assumes that we know a Gaussian process prior. And this is totally natural because, I mean, we're Bayesians and we want to, I mean, prior as a word to us means it's fixed and it's given when the algorithm starts running. So there's no, like, there's almost no notion of estimating the prior or unknown prior. But in practice, we do have these type of problems, right? We don't know how to set the priors. And once we don't have a prior, how do we know how good our approach is? So this particular work filled in that gap and shows that, well, if we don't know the prior, we can do some estimation and we're still good. So here we prove a regret bound. It has linear dependency on observation noise because, yeah, we're trying to choose the best observation instead of the best f, like the underlying function value. And then what we know from this here is that n, the dependency on n here, which means pre-training on more tasks lead to a better pre-trained model, which lead to a smaller regret, which is also easy to understand, right? If we have more tasks, then we will actually be able to learn the prior better. So there's also a dependency on t, which is the number of iterations of Bayesian optimization, which actually I forgot if I just explained why we call it HyperBO. It's because we are doing Bayesian optimization with all these learned hyperparameters or pre-trained hyperparameters. So yeah, the dependency on t is kind of complicated. Typically, in the regret bounds we have for GPU-CB or other Bayesian optimization methods, is that, well, as the more, the better. But here, the regret bound shows that, well, if we have more Bayesian optimization iterations, it actually pushes the posterior GP away from the ground truth posterior. But we still gain more information by observing more. Right, so notice that this only applies to the KL objective, and I mean, the more general case is still an open question, and I welcome everyone to take a look and see if you can solve it. All right, so in order to actually verify it, right? I mean, we talked about the kind of how we don't understand deep learning and we don't understand that much like hyperparameters for deep learning. And then after I joined Google, a bunch of us were like, well, let's actually do this particular problem where we had a bunch of data sets, like all these, like some of them can be really large, like ImageNet, 1B, WMT 15, it's a German to English, I think, transmission data set. And some of them, I think UniRef is like a protein one, I forgot. So, and then we train the near state of the art deep learning models, including like white ResNet, ResNet 50, Transformer, and so on. And then we use like different batch sizes to really simulate how things work in the real like hyperparameter tuning for these deep learning models. And we come up with this data set called PD1, it's a neural net tuning dataset. PD actually stands for prior discovery, which is the name of the project, the original name of the project. So yeah, we have 12,000 machine days of computation and 30,000 hyperparameter evaluations on these tasks and models. I mean, I think that's a really a luxury of industry, and that we open source everything. So yeah, please use it and make use of it, so that like we don't. It's still like something. Yeah, because it's there, and there's no reason not to use it, right? And people already generated these data sets.
May I
Yes?
ask a question on the previous? So it's not here what are the hyperparameters? Like what is the search space in those tasks? So is it just batch size, or like that part was not clear? I guess it's common hyperparameters across all the models. Is that learning rate or
Yeah, so they are actually the hyperparameters for the optimizers, which can transfer across all the models. So
like hidden parameters, hidden hyperparameters and stuff like that, you mean?
right. So if you look at the paper, like on my website, let me pull it up. Oops. Is this viewable? Okay. I'm actually not sure if it's viewable.
Yeah, you can see that.
Yeah. Okay. So, oops. So there are these variables, I mean, hyperparameters, the learning rate. So they're described here, their learning rate, momentum, the learning rate decay schedule, prior, the decay steps. So it specifies an optimizer that can be used across all the models.
Okay, cool, thanks.
Yeah, thank you. And we evaluated on this data set for our approach, which involves, so yeah, we abbreviated it as H-star, the HyperBO approach with both NLL and KL. Right, I forgot to mention in that data set, we actually have a pretty large percentage of matching inputs. In this case, it turns out the matching inputs becomes very important. So the NLL methods also incorporate these matching inputs, but it seems like it can't really benefit from it as much as the KL method. And then we compare to the single task off-the-shelf BayesOpt, MIMO, RFGP, which are contextual Bayesian optimization with some common, I would say, like neural network style of Gaussian process. And then there's the meta learning acquisition functions approach from pronouncing it right, I apologize if not, 2020, and the single task Bayesian optimization with hand-tuned priors on both parameters and UCB coefficients. So this one is actually, yeah, something where actually like people have actually tuned it very carefully by hand, and you can see that it actually performs quite well. So this is the performance profile, and y-axis is number of tasks, where it outperforms the median best error rate at 100th iteration, and x-axis is the Bayesian optimization iterations. So the higher, the better. And KL method is better than the NLL, and better than the STBOH, and better than the rest of the approach that doesn't use any good priors, I would say. Okay, so let me skip others. And then we also see very robust performance of the HyperBO approach, fewer training tasks. So the left one is number of training tasks. So we reduce it up to 3. So the total is actually 24, I think. So reduced it and train on some, I mean, we basically reduce it and then train on some test tasks and see what the performance is. So, I mean, what we see here is it actually didn't matter too much. There is a decrease on the regret on error rate by increasing the number of training tasks, but roughly, I mean, it's not by a large margin. And then when we decrease the number of training data, what we see is that it actually reaches the best performance when we have 5% of training data, and then stay very stay put like from there. But when we decrease to less than 5% of data, we get much worse performance. Okay, these are individual tasks. I can go back to this. Okay, so this is actually an important slide I want to tell you about, which is, so it really characterizes the how negative log likelihoods matters to Bayesian optimization. So in this case, we use these methods, I mean, the HyperBO one pre-trained on 18 irrelevant tasks. So they don't share the same like data set in terms of like, is a CFAR, is a CFAR 100. And then both HyperBO and single task BO trains on 100 randomly selected data points of the test tasks. So this row here, I mean, this column here is the model without any training for the test task. I mean, this is NLL on the test task only. So the test task include like 1,000 to 2,000 data points, but single task and the HyperBO NLL only trains on 100 ones. And you can see that like if we train on 100 data points, like a lot of times for the single task Bayesian optimization, which is our typical off-the-shelf BayesOpt, we get even worse negative log likelihood for like comparing to no training. And then if you look at the negative log likelihood on all the tasks, again, like single task is comparing to like these numbers on NLL for all the tasks without any training, it actually becomes worse because we trained on the 100 data points. And then you observe very similar behavior on the KL divergence on the matching data, I mean, the matching inputs. But I think it really tells us, what it tells us here is, let's not use type 2 maximum likelihood to optimize our Gaussian process in Bayesian optimization. Yeah. Okay, so there are some results on sensitivity to acquisition function. Actually, I want to reiterate again in the previous slides, I was talking about maximum type 2 maximum likelihood if we define the GP and tries to learn its hyperparameters on the mean and kernel. It's a different story if you use a hierarchical GP where you have priors on the hyperparameters for mean and kernel. Yeah, just a disclaimer there. Okay, so let me skip this. And we also looked at different objective functions, including adding the NLL and KL together. I mean, in this case, it doesn't show a lot of difference because we have a lot of, I mean, we have, I think, around at least 500 matching data points, I mean, matching inputs across all the tasks. So yeah, and a little recommendation here. So both KL and NLL objectives work in the continuous search space, but KL assumes that we have the same inputs across tasks, and NLL is more flexible. So there are a lot of trade-offs here. KL can be easier to interpret, like for example, it's the number of extra bits or nets to encode the multivariate Gaussian. And then notice here that KLL on the data set is not NLL on the same data set because the negative log likelihood can't really use the matching inputs the same way as KL. I can explain more later. So yeah, roughly, if we have a relatively large set of observations on same inputs across tasks, I think KL would work better. And if not, there's no same inputs, then we can't use KL. So yeah, just use NLL. And if there's also a possibility to combine them and treat the KL objective as a regularizer a bit, because like if you look at the KL, it does look like a regularizer because we are trying to minimize the distance, like almost like the divergence between the estimated multivariate Gaussian and the multivariate Gaussian induced by our GP. Okay, so right, there's code, there's data set. Yeah, please let us know if you have any questions, and you can report to the issues of on our GitHub page. And I just want to acknowledge like all my collaborators. So the most recent one that we are like the paper we worked on is pre-training helps Bayes optimization 2, the title of the talk. And yeah, there actually George worked on the data set with a lot of effort. So I really hope like people can yeah, can use the data set so that like, our effort don't like goes into waste. And then previously, this is a 2018 paper on regret bounds for meta Bayesian optimization with an unknown Gaussian process prior. And this is my colleague Bonjun Kim and my PhD advisor Leslie Caping, and there we are looking at the regret bounds. It's a relatively dense paper, but I think we understood a lot after we looked at the regret bound. Okay, some advertisements. We actually have a Google BayesOpt speaker series. If you would like to speak there, like please let me know. And we also have a GP seminar series co-organized with a different group of folks. And we still have several talks coming up, like the one from my colleague Balaji on SNGP, and then the later one, I think it will be by Zubin later this month. All right, thank you, and please let me know if you have any questions.